All right, guys. No promises. My kid isn't gonna scream and wake up in the middle of this, but I'll do what I can. So bonding, which is unit 6, I guess. Here's what you need to know. You need to know the difference between ionic bonding and covalent bonding. Ionic bonding is between a metal and a nonmetal, and covalent bonding is between two nonmetals. Ionic bonding, the electrons are transferred, and covalent bonding, the electrons are shared. Okay. Examples of things that are ionically bonded are MgO, NaCl, CaCl2. Both of those, all of those have a metal and a nonmetal. Okay. Covalent bonds are going to be something like water, which are two nonmetals, carbon dioxide, which are two nonmetals, CH4, which are nonmetals, etc. Okay. Ionic structures, when you draw their Lewis structure, you draw them as ions. Okay, so for example, like MgO, Mg as an atom has 2 valence electrons. Oxygen as an atom has 6 valence electrons. Magnesium is looking to lose 2. One goes there, one goes there. All right. So that becomes the Lewis structure for an ionic compound. Magnesium has no valence electrons, and it has a charge of 2 plus. That comes from your periodic table. And oxygen has 8 valence electrons, and it has a charge of 2 minus, or minus 2, it doesn't matter. So those charges there come from your periodic table. They're their oxidation states. If you were doing something like CaCl2, for example, okay, calcium has 2 valence electrons and chlorine has 7. This is why you need 2 chlorines for 1 calcium. Okay, you don't have to draw it twice, though I'd love for you to draw it twice. Calcium there is going to have no dots around it and a charge of 2 plus. And then you're going to have a chlorine, which has a charge of minus 1. You need 2 of them, so you can put a big 2 in front like that. Or if you don't want to put that 2, you can draw another one. Make sure your anions, okay, make sure your anions have 8 and your cations have 0. Okay, so anions should have 8 electrons and your cations should have 0 electrons. All right. That's pretty much all you need to know about ionic bonding as of right now for this test. Covalent bonding becomes a little bit more complicated because covalent bonding is where we start talking about bond polarity and molecule polarity. But first, let's talk about Lewis structures. When you're drawing Lewis structures for covalent bonds, what I want to make sure that you do is that when you're drawing them, you spread them out before you double them up. Okay, and what I mean by that is if I'm drawing H2S, for example. So here's S. S has 1, 2, 3, 4, 5, 6 electrons. And then I know that hydrogen has 1, and I have 2 hydrogens. That's going to form a bond, okay? And that's going to form a bond. Now be careful how you write them, okay? So a lot of you have been doing something like, oh, that's cool, like this. Okay, and I see exactly what you're doing, but be careful because one line equals 2 electrons and a dot equals 1 electron. So if you're looking at this right there, that essentially is representing 4 electrons. If you'd like to play connect the dots, you need to make sure that you connect them all the way or just turn them into one big line. Okay, or you can circle them like I did there. Either is fine. If you're doing something like CH4, start with the middle atom. And then you see where the lonely ones are. Remember, we're matching our lonelies. You see where the lonely ones are? As a matter of fact, I'm not going to do CH4, I'm going to do CF4 because I think it's going to be more helpful for what we're going to talk about next. So here is carbon. Carbon has 1, 2, 3, 4. And it's got 4 fluorines around it. Each fluorine has 7. And what I'm going to do, instead of drawing lines, I'm going to circle those bonds and be like, there they are. All right, so that carbon is making 4 bonds, 1 to each fluorine. Now, we need to talk about bond polarity and we need to talk about molecule polarity. So let me move that right over there. Bond polarity is based off of electronegativity difference, okay? END, electronegativity difference. When I'm talking about bond polarity, what I want you to do is I want you to look at just one bond. This molecule that I drew right there is made up of more than one bond. It's made up of 4. But I'm looking at just one bond, that one right there. The bond between carbon and fluorine, okay? All right, is that bond polar? Okay, it's polar. Oh, apparently this is green now. It's polar if they have an END that is greater than 0. That means, are their electronegativities the same? If they're the same, then it would be nonpolar. If they're different, so if they have different electronegativities, then it's polar. Okay, it's a nonpolar bond if your electronegativity difference equals 0. Okay, and when are you going to see that? You're going to see that in things like Br bonded to Br. You're going to see that H bonded to H. That's not an H, that's an F, but there you go. Okay, you're going to see that in I2. You're going to see that in N2. When your electronegativity difference is 0, it's the same thing bonded, okay? That's when the bond is nonpolar. So most bonds that we're talking about are polar, okay? This applies to covalent only. Okay, it does not apply to ionic. Ionic is ionic. This is covalent. And when we talk polarity, what we're saying is that the electrons are not shared evenly. That means that the fluorine gets the electrons a little bit more of the time. Don't worry about what that symbol is. I forgot that I didn't really show it to you. So fluorine becomes slightly negative and carbon becomes slightly positive. And since they're not sharing the electrons equally, it makes the bond polar. It makes it like a magnet, or like the poles, right? It's got a positive pole and a negative pole. All right. The last thing we need to talk about is molecule polarity. And apparently I'm going to do that way down there. Okay, when you're doing molecule polarity, you're looking at the symmetry, and it's the radial symmetry of the molecule. We're going to remember SNAP. That stands for symmetrical nonpolar, asymmetrical polar. What I want you to do is look at the center atom, which is that carbon right there. Okay, look at this guy. Is he bonded to the same thing on all 4 sides? We've got fluorine, 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 fluorine. Since it's the same thing, same on all 4 sides, that means it's symmetrical nonpolar. Okay? If it's something like what we drew before, H2S, okay, that S in the middle is bonded to hydrogen, hydrogen, nothing, nothing, okay? That makes that asymmetrical polar, which is the AP in SNAP. Okay, things that if you're one that likes to memorize, really, really common ones, okay? CH4 is nonpolar, CF4 is nonpolar, NH3 is polar. Let's do H2O is polar, CO2 is nonpolar. NH3, if you want to check it out, there's N, it's got 5. There's H. All right, I'm looking at the center atom, which is my N. It's bonded to hydrogen, to hydrogen to hydrogen to nothing. So that's asymmetrical polar. Okay, it is an uneven distribution of charge throughout the whole molecule. So if we want to go back, we can look at the CF4 here, right? Oh, that's weird. Look at that. Okay, so here's that CF4. The bonds are polar. We already said that the bonds are polar, right? We said that fluorine gets those electrons more of the time. But this bond's polar too, so it essentially, they cancel each other out. So this is a great example of something with polar bonds, but is a non-polar molecule, because they're based on different things. When in doubt, draw it, okay? Draw it. If you're not sure what shape it is, what polarity it is, draw it, and I think that will help a lot. Hopefully this was helpful. The last thing you need to know, forgive me, is that when is barf, okay? Breaking bonds absorbs energy, releasing forms. So when you form a bond, you release energy. When you break a bond, it absorbs energy. So if I'm forming a bond between an oxygen like this, I'm going to expect energy to come out, okay? Because I'm forming a bond, so this is releasing energy. And then when I'm breaking a bond, so like if I have F2 turning into F plus F, those F's are happy together. They like to be together. So to separate them, energy has to go in. Okay, that would make that endothermic. And that means that energy is absorbed when you're breaking a bond. Remember when I broke the pencil. Hopefully that's helpful. Good luck.